Okay, so we start with conic sections. What's a conic section?
It can be a plane intersected by two pyramids with circle bases.
What are those called? Cones. Yes. Conic sections. Cone sections. So it's when you intersect a plane with a double cone. What was the first conic section we looked at? Circles. And then? Ellipses. And then? Parabolas. And then? God bless. All right. Okay, so it's just those four sections. That's it. A circle was defined as. Raise your hand. Go, Peter?
The set of all points equidistant in a plane either.
Yes, the set of all points in a plane equidistant from one center point. Right? Should be in your notes. The set of all points in a plane equidistant from a center point. And if you have it centered at the origin, at some radius r, you get a characteristic equation of formula for a circle.
You don't have like the stuff in the denominator, or maybe you do. Yeah. Well, it's a circle.
R squared equals x squared plus.
Someone's saying it over there.
X squared plus.
Alan, what is it? R squared. All right, team, bring it together. Yes, x squared plus y squared equals r squared. That's the equation for a circle centered at the origin of radius r. What about a circle off-center? At some point, centered at some point hk of radius r. X minus h squared. Go ahead, Dylan, you're doing it.
Plus y minus k squared.
Let me just. Yep, y minus k squared. Square r to the fourth. I'll simplify that for us. Thanks. Yep. So pretty simple. So circles. All right. Then ellipses, they kind of look like circles, but they're just a little bit stretched out. So an ellipse is the set of all points in the plane such that, you know, Guadi?
I don't remember.
That's okay.
I know it, but I don't.
You know it, but you don't. Yeah. Let me just draw an ellipse for us. What are some important points of the ellipse?
The center.
Okay.
There's the center, and then there's the foci. I haven't said it yet.
Oh, it's the sum.
The sum of distances from what to what? Okay, so the sum of the distances from two fixed points to any point on the ellipse is a constant. So like if you picked any point, if that's f1 and f2, and here's some point p on the ellipse, if you do this line and this line, then f1p plus f2p equals some constant. And what was the sum? What did we say? That the sum of the focal radii equals what?
Formula.
Yeah, the formula. What length does it end up coming out to? 2a. Well, that begs some questions. What is a?
Oh, the tiny line.
No. It's not the tiny line.
This way.
A is from the midpoint to the edge.
To
It's like this.
the wider one. Yeah, it's the semi-major axis. What?
Oh, yeah.
Oh, yes.
Oh yes, it's all coming back to us. So A, think of it, right? Don't be overwhelmed by big words. Semi means half. Major meaning the longer one. Half of the longer axis. Half longer axis. Semi-major axis, A. Semi-minor axis, half of the smaller one, B. Easy. Easy as pig. Okay? And then, so if you have an ellipse, so this is a true thing about the sum of the focal radii to any point on the ellipse. And remember when I did that earlier in the year and I had the string out and we drew the ellipse on the board? It's so cool. You should do that as a way to celebrate the end of the year. Show your family. So then if it's centered at 0, 0, what does the equation of the ellipse come out to? Yes. Equals? Equals? Yes. Good.
And then it's x squared. Oh no.
And we leave it so the thing is that if the ellipse is horizontally oriented like the one I just drew, or if it's vertically oriented, we always let the semi-major axis be A. So so then if it's oriented this way, then the long one is A and the short one is B. And so, okay, so this one goes to the one up here. But what would the equation of that ellipse be? Yeah, there'd be a y squared over a squared, and x squared over b squared equals 1. And really there's no need to get confused about it. You just, the x squared goes over the x part, whatever it is, and the y squared goes over the y part, whatever it is. Okay, that's ellipses. Ooh, what if we have it shifted to some point hk? Let's say we have these dimensions so that the semi-major axis is A, the semi-minor axis is B. Ian, it sounded like you were saying it. X minus h squared. Over what? Uh-huh. Equals? Perfect. Thanks. Nice. Nice. Not bad at all.
What day is our final? Tuesday?
Oh, I think yours is the...
Tuesday.
Oh, it is Tuesday. That's right. It's the A block has it the last day. Okay, so ellipses, just the general aspects of it. Let's go to parabolas. By the way, this parabolas is kind of exciting because this is the first time that you were able to actually know what a parabola was in your life. You've had a lot of moments like that in this class, but this is just one of them. God bless. The set of all points in the plane. What? Equidistant. Yes. So I'll say it like this: equidistant from a fixed point. Well, fixed line. I guess, Dylan, you were right. I guess they're both fixed. Fixed this, fixed that. Fixed line.
From a fixed line and a point normal.
So then if we drew a parabola, let's say that this was our parabola right there. What do we call that fixed point? The focus. It's foci is plural, just so you get your grammar right. Focus, singular, foci, plural. Wouldn't want any grammar errors. Okay, so that's the focus. Okay. And what do we call that line?
IX. Determinant.
Not determinate? Someone's saying it, I think.
The matrix.
Directrix. You said no. IX. So the thing is, you pick any point on the parabola, any point you want. You draw a line from that point to the focus, draw it down to the line, they're equidistant. So I'll put this as like, let's call this point D, let's call this point P. So we have that PF equals PD for all points on parabola. That's how we got the equation for the parabola, starting with that fact, using the distance formula. We started there. It was pretty awesome. We were figuring out so much. Conic sections is one of my top. I really like conic sections. Okay. So, well, for a vertically oriented parabola, we have this equation. Y minus something equals something times x plus or minus something squared. Fill in the blanks. Anyone know? Minus k. Yes. And that point A, that was a special variable, right? What do we call, we had a formula to get A or to relate A to other things, right? Oh, it's all coming back. Where force C was what? The directrix and the vertex? Yes. Distance between, you could say either, oh, let me fix that. I'll put a braces. Distance between directrix and vertex, or focus and vertex. So on our picture we have that this is C and this is C. Old hat. Of course it is. So that's a vertically oriented parabola. But we could also have a horizontally oriented parabola. We could have something like that. So here's our center, focus, our directrix. So we still will have a C, which is that distance from vertex to focus or from vertex to directrix. We still have an HK as the vertex. How do I write my equation though? X minus what? H equals. Ellen's on it. Thanks. Yep. Okay. And just be careful, remember that this A, this constant out front, if the A here is positive, it means what? Opens up. If it's negative, down. And remember, so if it's up, then the A is positive and the C is positive. So remember, these have to be the same sign. Same sign. Just keep that, in your mind if you're ever using C for calculations. It needs to have the same sign as the A value. And likewise for the horizontally oriented parabola, that A is positive if it opens right, negative if it opens left. Parabolas. Questions on that? What about hyperbolas? Oh wait, what's the last conic section? Hyperbolas. Hyperbola is the set of all points such that the difference of Alex has perfect memory. The set of all points in the plane such that the difference in distances from P to two fixed points is a given constant. What do we call those points? Foci. Yes, it's still foci. So a hyperbola is going to look something like two branches Where are the foci in relation to those branches? Above and below. Yep. So there's a focus here and a focus here. Call it F2, F1. And then if you pick any point, let's call this P, on the hyperbola, and draw lines to go from F1 to P, and then F2 to P, the difference between those two distances. So when we can, just to make it always a positive difference, we can say something like this, that the absolute value of F1P minus F2P is a constant, which we found out was what? So many formulas. No. You're close. Farther. Farther. Oh no, farther, farther. 2A. You just needed more of what you were already saying, Ben. You already said A, just say it again. A and A. So the difference is a given constant. Is this ringing a bell? No? Oh, I'm pretty sure I taught this. Yeah, let me just.
Can you share that with us?
Oh, you want the good stuff. These are all posted. They're just further up the chain. I already did post it. If I added up all the time it took to post every page of notes, it probably took me several hours this semester. So I don't want to do it again. So I wrote it here, right? The difference of focal radii is 2A. So there you go. See, these notes were written on January 4th. Wow, y'all were so much younger back then. Okay, so I did tell you at one point in time. Yes, correct. Got it. Thanks. Okay. So now there's something a little off in my drawing. That's right, I said it. There's no box, and there's nothing that the whole box is for, which is to draw the asymptotes. The asymptotes. God bless you. This does not look like it's asymptotically approaching some line, but it's supposed to be. That's right, that's an adverb. Need the box. The box is the best part. Yeah, just don't mess up. So remember about the box. It's simple. Whichever side is longer is A. And maybe I should pull these notes back up for a second. So to save us a little bit of time here. Right, so if we're centered at the origin, for a horizontal, we call the focal distance C. The different distance to the focus is C. And you see that if it's horizontally oriented, the A goes under the X. If it's vertically oriented, the A goes under the Y. So actually, whoever was saying whichever one's bigger is the A, that's true for ellipses.
Who said that?
Who said that? Dylan, Carol.
He speaks.
Okay, so it's actually whatever's under the X is it should be whichever one's first, right? It's the orientation that determines which one's the A. Eleanor's like, too many different things were said. So let's see if we can sort it out. See, there's a horizontally oriented one on the left. You see it? Andrew, you see it? Robert? Okay, great.
Is the
Hold on. Wait, let me finish. So this is horizontally oriented, so the A goes with the X. This is vertically oriented, so the A goes with the Y.
Gotcha.
So it's, but in other words, whatever is under the X, you draw on the X-axis. Whatever's under the Y, you draw on the Y. Yeah, just think of it like that.
So if the A is on the X, you put it under the A. If the, or the F. Okay, so the A is on the X, you put it under the X.
Yes.
And then if the B is this way, you put it under the Y.
That sounds
If the A's there,
right.
you put it under.
Yes.
I got it.
He's got it. All right, good. Does someone else have a question?
Is the difference between the two vertices 2A?
Yes. Not wait. Sorry. Difference between two vertices. It's the difference in focal radii is A. 2A. Right? The difference between two focal radii. Which one there? Difference between two focal radii is 2A. And then notice this. Let's fill in. So, in this picture, then, so we would call this one A. This one B. So this would be a vertically oriented hyperbola, y squared over a squared minus x squared over b squared equals 1. We have that the difference in focal radii is 2a. And then this other thing which we forgot to mention with the ellipses was the relationship between a, b, and c. So with the hyperbola, we have this relationship, c squared equals a squared plus b squared. That's right, it's minus for the ellipses. So c squared equals a squared plus b squared for hyperbolas. And it's minus for ellipses. So let's go add that back with ellipses, since we seem to have omitted it.
Is the A distance of like the box or from like both sides?
So the A is the distance from the center to the vertex, which is the side of the box. Yes. Well, I mean, I guess it's half of the side of the box, because it goes on both.
Yeah.
You know what I mean? Yes or no?
So what's the C in that verse? Is it the horizontal to
Yes. C is the focal length for all of these, which is the distance between vertex and focus. Distinguished from the focal radii, right? The focal radii means the difference from a point on any point on the ellipse or whatever to the focus. But focal length is vertex to focus. Yes?
So, can I show you, like, on here, is A from here to here, or from here to here?
Where you have it.
Okay.
Okay. All right. All right. So that's conic sections.
Okay, we're good now.
That's the most distant thing for all of us. It's been a while. All right. Polynomials. What do we learn about polynomials? We start off with the easy thing, right? Remember we started off with just the quadratic formula? Which you know. Yeah, which is
B squared plus or minus the square root of million. Or it's negative B plus or minus square root of B squared minus 4AC all over 2.
it's just you need to start say it fast enough. That's how you get it out. If someone stops you, then you can't get it out. Yes.
So you know that thing where we have to solve like the formula for a parabola where you start with PF equals PD?
Yep.
Like, could we go through that?
Oh, so Dylan's asking if you have a parabola, and you're saying that we know some point on it and where the focus is and where the directrix is.
Yeah.
You want to just give us the problem?
I don't have a problem, but like,
You're just thinking of it.
yeah.
Let's save that for now. Yeah. Yeah, because that'll get into a lot of the specifics, which I want to avoid for now. Just trying to do the most general overview. What does this formula tell you about a parabola? X-intercepts. What's another word for x-intercepts?
Zeros.
The zeros, the roots.
Zero.
Or if the parabola is given by f of x, it's when the solutions to the equation f of x equals 0. These are all different ways of talking about roots, intercepts, zeros, solutions to f of x equals 0. They all mean the same thing. Okay, so how do we use this formula to get special information besides just the intercepts? Yeah, Dylan.
Negative B over 2A is the x coordinate of vertex.
Yes. X chord of vertex. That was helpful. Yep. That was really nice. So then you can just plug that in real quick, and then you can then plug whatever number you get, plug it back into the equation to get the y value, and then you have the vertex. You get the vertex, the two x-intercepts, the y-intercept, boom, boom, boom. You're ready to graph. Yes, sir. Yes, sir. Okay. So those were parabolas. And then we moved on to general polynomials. However many, x to the third, fourth, fifth, sixth, whatever. And remember, the challenge was, how do you solve the polynomial? How do you solve it? Right? Which again is this question. How do you find out, how do you factor it so then you can get the roots and then graph it and analyze it? So we learned several different techniques for figuring that out. So let's list them out for a second. So we learned long division, or we reviewed long division, not learn it, and synthetic division. Mm-hmm. Right, and so that was like, if someone could tell you, they're like, hey, Jack, I think that this is a root of the equation. You're like, okay, synthetic division. Oh, if I get what? What do you have to get at the end of it to be?
0.
0, then you know it's a factor. And so you can factor it out and move on. Right? So, but then remember, we confronted this big problem, which was, okay, that's nice if I have a special voice whispering in my ear. Try 2. But what if you don't have someone whispering to you, try these numbers? Yes?
Use the factors with the coefficient of the first term and the last one. You do h over k.
Yes. So this was called the rational root theorem. Yes. So basically, this was the idea that you could narrow down, instead of looking at an infinite set of numbers and guessing, you could then narrow it down and say, well, if there are rational roots, there are only a certain number of candidates. And so you got those by taking, so let's say we had, I'll just write out a general, ax cubed plus bx squared plus cx plus d. You're trying to solve this equation. You would take factors of d, so we'll say that h is a factor of d, k is a factor of a, and then test out all of those h over k. Test out all those combinations. So like, for example, if our equation was something like, I don't know, 3x cubed plus 10x squared plus, let's say 11 equals 0. Okay, what are the factors of the constant term? Constant term? Yeah, 1 and 11. Factors of the leading term? 3 and 1. So we would test out plus or minus 1, 3, oops, I don't know why I did that. 1/11th, or sorry, wait, I'm going backwards. 1 plus or minus 11 plus or minus 1/3 plus or minus 11/3. That's better. Take the constant term factor over the leading term factors. And then so you have 4 things to test out. That's nice.
What about 30?
There's no way you can take either 1 or 11 and divide it by 1 or 3 to get 3. So you take the factors of the constant term, 1 or 11, and divide those by 1 or 3. So 1 over 1 is 1, 1 over 3 is 1/3, 11 over 1 is 11, 11 over 3 is 11/3. There's another thing we had to narrow things down, is called something about signs. Looking at the sign changes.
The differences in signs. Like,
Ellen said it, Descartes' rule of signs. So Descartes' rule of signs. So you just look at the sign changes. So let's just say it out loud. How does it work? Someone raise your hand, tell me. Descartes' rule of signs. Wadi?
It's when you look at whether it switches like plus and minus, and you count how many times, and you subtract how many times to get the infinite positive and negative.
You have a lot of good stuff there. I don't know what the infinite positive negative means.
I think I'm thinking of something else.
Okay, that might be. Well, the first part's good though. You're going to count the sign changes. That's good. Thank you. Dylan, do you have the last part?
You change it to negative. Change it to negative x, and if the degree is odd, you flip the sign on the side.
That's right. That's right. So, if you can, God bless. God bless. So you look at the actual original polynomial. Count the number of sign changes. Okay? 1, 2, 3. So there's 3 or 1 positive real roots.
how do you get the 1?
You take whatever number of sign changes and subtract 2, or subtract another 2, or subtract another 2. So if you got 5, it could be 5 or 3 or 1.
Gotcha.
If you got 2, it could be 2 or 0. What if you get 1?
0, I guess.
Nope, just 1. 1 minus 2 would be negative 1.
Or 0.
Oh no, should say 1. You're like, Mr. Williams, called you out. Bad logic. Thanks, Robert, for correcting me.
Sorry.
No, thank you.
I saw it on the thing.
You helped me. Thank you. I'm not upset. I'm glad. I could mislead generations of students if this was not fixed. I'll have my future students write letters to you. Dear Robert, you saved me from many errors. Okay, so you count how many sign changes from the original thing. That tells you how many possible positive real roots. Then you put in negative x for all of your x's. Right, so if there's odd powers of x, it switches the sign. Then you count how many sign changes. That tells you how many possible negative real roots. Easy. Okay, so that was Descartes' rule of signs. Anything else? Yes, Hazel?
Isn't it like the leftovers from the value of the degree are like I? Do they not get?
Oh, yes. That's a really good point. So what she's saying is that, let's go back to this. So this is how many possible positive real roots and negative real roots. So it doesn't say anything about the imaginary roots.
You're gonna
Right.
make a little box thing.
Yep. So like for this one, if it has degree 6, there's got to be at least 6 roots. Some of them can be real, some of them can be imaginary. Yes, and Young?
Doesn't the number of imaginary roots have to be
Yes. Yes. Imaginary roots. Whenever we have real coefficients for our polynomial equation, as long as the coefficients are real, which is what we've been doing, then yes, you have at least pairs of imaginary roots. So like for example, for this one, you would do, you say, okay, there's 3 or 1 positive real roots, plug in the negative x, 1 negative real root, make a table, how many positive real, that should say negative real. Gosh, who let this thing go? Robert, where were you? Okay, so like for this one, it's a 4th degree, so it's got to have 4 total roots. So if you have 3 positive real, 1 negative real, there's 0 imaginary. But if you have 1 positive real, 1 negative real, you have 2 imaginary. Yes? All right, let's go. I need your help though. I might mess up again. Okay, any questions on that? That was good. Imaginary roots. Okay, and then we can graph stuff, right? You figure out all the roots. Got it. Put those x-intercepts, get the y-intercept by just plugging in 0 for x. Boom, boom, boom. You know how the end behavior goes, right? Someone, help Dylan. How does the end behavior go for a polynomial? How do you figure it out? Degrees even.
Then they're the same.
Same direction, so both up or both down. If it's odd,
Up or down.
one of those. So how do you for an even one? How do you know if it's up or down down?
Negative.
First term, negative or positive. Yeah, so positive leading coefficient up, negative leading coefficient down down. What if it's odd degree?
Odd degree, it's to the right, it's up, and then the left is negative. If it's a negative coefficient, it's flipped.
That's right. Wish you people could see all of our hand gestures. You'd really benefit people on YouTube. Okay, great. All right, so that's basically polynomials in a nutshell. Topic number 3, exponentials and logs. Yes, Dylan.
So if it's like this, is that an odd negative?
You're saying if it's like this,
Is that odd degree negative?
yes, odd degree, negative leading coefficient. Man, what if the whole year could have gone this fast? We could have done like 20 times the amount of topics. We'd be through BC calculus by now.
First quarter, it's something more.
It's because you have to grow. So you actually have grown a lot. So that's why this is seeming so easy to you right now. There's this like. Okay. Exponentials and logarithms. Let's just, since we just have minutes, let's just talk about the general shapes of the graphs. So y equals, let's say, some exponential, b to the x. It looks like what? Ian's got it. It looks like this. Hardest one? Now that's assuming that b is what? Not just greater than 1. We actually don't deal with negative exponentials. So like a negative base raised to an exponent.
Oh, that's right, it's like 1/2.
Yeah. Oh, so if b is between 1 and 0, then it would look like a decay. Right, so this would be something like y equals 1/2 to the x. And you know that that's connected because 1/2 to, you see this is connected with the general thing, like this could also be written as what? 2 to the Exactly, negative x. So, and this could be like 2 to the x. So that's the exponential curve, exponential decay, growth. Okay, we'll do the logarithms before you leave. Intercept is where?
0, 1.
Not 0, 1?
1, 0.
1, 0. And it looks like this. Because it's the inverse of the exponential. What? And then we also looked at this kind of special case, ln absolute value of x, where you could do something like this. Like that. Any questions? Was that helpful?
Yeah.
Okay, you're welcome. Yes, Hazel. I'll post this. If I'm assuming it recorded.
On YouTube?
Like and subscribe. Yeah. Yes.
Like where you